Yesterday we have seen the integral mode of a PID controller. We have seen that it is function of old error. Integral mode is function of old error. Yesterday we have seen one example that suppose you want to drive a car at 60 kilometers per hour, that is set point. But initially PV also 60 kilometers per hour. But because of wind, it reduces to 55. Therefore, error equal to 5 kilometers per hour. You are giving additional input to compensate this error. Now, the new set point, PV new, becomes 60 kilometers per hour. But you are giving additional input. That additional input is function of this 5 kilometers per hour. Now there is no error. Now there is no error. There is no present error. This 5 kilometers per hour error is old error. This is old error. That's why integral mode is function of old error. How to obtain that? For that, suppose you are having a system that has error means, if you plot error introduced, this error will be integrated. Therefore, M of t starts increasing. M of t starts increasing because it is function of integral of E of t dt, integral mode. That's why as M of t increases, it starts decreasing. Suppose it comes again to the set point, the error becomes 0. Till then, the controller output will increase. The controller output will increase. That's why M of t keeps on changing until the error becomes 0. The M of t keeps on changing until the error becomes 0. Integrator continuously integrate the error to increase the controller output. That's why the integral mode completely eradicates the error. So if you use integral mode, there is no offset. Offset or steady state error, both are same. Offset, steady state error, both are one and the same. No offset for integral control. Integral control also can be called as proportional speed floating control. Proportional speed floating control. Since the rate of change of controller output is proportional to error. If error is large, the controller output will be large. If error is large means controller output will be large. It is proportional to error. The speed at which it increases is proportional to error. The speed at which the controller output increases is proportional to error. That's why it may also be called as proportional speed floating control. Proportional speed floating control. But we are not using as integral of E of t alone. It is multiplied by Kc by Ta. Or it can be called as Ki integral of E of t dt. This Ti is in seconds or in minutes. The unit of time is seconds or minutes. That's why we cannot give 0. Ti should not be 0. If it is 0 means what will happen? It becomes infinity. Divide by 0 error you will get. You cannot put the Ti equal to 0. That's why if you want to use only P only means we have to remove this integral mode or we have to remove the integral mode from calculation, or we can enter the largest value. Suppose the largest possible value 4-digit means we can enter 4 nines. That is also possible. So that it will be negligible. It will be negligible. Almost we are dividing the controller output by 10,000. That's why it is negligible. Or we can, there is a provision to turn off that integral mode. That way we can. In some controllers, we have to enter TI inverse. You have to enter TI inverse. In that case, we can enter 0. Because TI inverse, 1 by TI we are entering. That's why we can directly put 0. Now, let us simulate. This is, let us put here only P only controller. P only controller, a 4th order process. That's why ultimate gain is 4. Ultimate gain is 4. P only controller means 2. We'll make this is 0 because 1 by Ti, Kc by Ti can be given 0. Derivative mode also 0. We can enter. This is integral mode. Here, let us enter only, sorry, here it is in proportional mode. Here we are entering only integral mode. Integral mode, let us put Kc by Ti. So let us simulate. We are giving a step change. Initial value 0, final value is 2. Let us make it 1. Final value is 0. Final value is 1. No disturbance is here. So if you simulate, in the first simulation, we are having only proportional control. You can notice here. You can notice here. We entered proportional only. We made K equal to 0, D also equal to 0. It means only proportional controller. The response is in yellow color. Here, we selected only integral mode, and we entered only Ti. Ti is in the denominator, that's why 1 by 3 we entered. If you see the response, for integral mode, it is settled at 1. What is the set point? 1. It is settled at 1. No problem. If you see the P only controller, only proportional controller, it is settled at about 0.6. It's settled at 0.6. Steady state error is there. If we compare these two, here only we used only integral mode, no Kc. That's why we entered 1 by Ti only. In that case, if you compare these two responses, what is the difference? If you use integral mode, no steady state error. If you use P only controller, steady state error is there. But if you see the raise time, for P only controller, raise time is better. But for I mode, it takes a sluggish, takes a long time to raise. Raise time, if you see that it is greater value. So the system becomes sluggish. To make it smart, only we are including proportional controller. So why the combination of P plus I is used is to make it smart. But I mode alone is sufficient to remove the steady state error. So now let us make that proportional only controller into PI controller. If we made this PI controller, then it should be multiplied by 0.45. 4 multiplied by 0.45. So we entered KC. TI is 0.45, 0.45 multiplied by 4. That is KC. Divided 5. So we have to enter 5. So the PI controller, here we entered. Here only I mode. Now let us see the simulation. See the response. I mode is sluggish. But if you use P as well as I, it becomes smart. It quickly comes to raise time is reduced. Overshoot also reduced. Overshoot also reduced, quickly settled. That's why we are using PI. Settling time is reduced, overshoot is reduced, raise time is reduced. That's why instead of using I mode alone, we are using P plus I mode. But P mode, there is no use of P mode when error becomes 0. When error becomes 0. Suppose in I mode, I am, what is that? Note down this ISA. ISA is 11 and ISE is 5.87. You note down. Now let us slightly increase the value of multiplied by 2 times. I'm increasing this 2 times. What happens? Let us see. We are increasing this by 2 times. It becomes unstable. Let us increase 1.5 times. Let us increase 1.5 times. We are increasing 1.5 times. So if you increase too much, it becomes unstable. Now it is stable. If you increase Kc by Ti, it means you are decreasing Ti. If you decrease Ti, oscillation increases. If you decrease Ti, oscillation increases. Number of settling time increases. So if improper value of Ti will lead to oscillation, because if you decrease Ti means you are increasing gain. That's why oscillation is more. On the other hand, now what we did, we increased, that is we decreased Ti. We decreased Ti. If you increase Ti, what will happen? Increase Ti means instead of 1.5, let us put 0.75. 0.75 means you increased Ti. What happens? Now let us see. What happens? We are taking PI controller as standard. With that, we are comparing. Now, oscillation reduced. So, if you increase Ti, oscillation reduced. It means that Ti is changing the zeta value. Changing the zeta value. If Ti decreases, zeta also decreases. If Ti increases, zeta also increases. Ti increases means zeta also increases. Ti is in the denominator. Note down that Ti is in the denominator. If Ti increases, zeta also increases. Ti decreases, zeta also decreases. That we can notice here. So we are comparing with PI controller. But anyhow, there is sluggishness is there. That is not changing. So to make the system smart, we are including proportional mode. If you use proportional only mode, it is smart. That's why can we remove integral mode? If you use P only mode, means there will be a steady state error. That's why we are using P as well as I mode. What are the other drawbacks with integral mode?